Good afternoon. Welcome to today's SCA webinar with Dr. John Rosine on Deepwater Sedimentation. Before we start today's webinar, we'd like to ask a couple of polling questions to learn more about the demographics of our audience. So the first question is, what's your primary discipline? Let's see who's attending. Looks like we have quite a few geoscientists in the crowd, no surprise. Looks like it's about 80% geoscience, 20% petroleum engineers so far. Got most of the responses, so I'll go ahead and close the poll and share the results. 81% geoscience, 19% petroleum engineering. So our next question is, how many years of full-time experience do you have in the upstream oil and gas industry? Looks like we've got a pretty good distribution. Someone in almost every category. Most of you have voted, so I'll go ahead and close the poll, share the results. We have 28% with 1 to 10 years, 21% with 11 to 20 years, 21% with 21 to 30 years, and 31% with over 30 years. So good distribution, except no one in the less than 1 year category. So let me share my slides here. So before I introduce Dr. Rosine, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature, and we'll cover the Q&A at the end of the presentation. So the topic today is Deepwater Sedimentation. Our speaker is Dr. John Rosine. He is president of Basin Dynamics. He's also a professor adjunct at University of Houston. He has quite a bit of expertise where he's worked in a variety of basins with experience in development, drilling, exploration, competency and training and consulting. And he served frequently as a lead geologist. He currently serves as chair of the Houston Explorers Club. Dr. Rosine received his PhD from Stanford and a BA from Colorado College. So the course that he teaches for SCA is called Applied Deepwater Sedimentology and Stratigraphy. You can see a description there of this 5-day course. It's offered in an in-person format in SCA's Training Center in Houston, October 11th through 15th. And of course, it's also available for in-house training as well. So contact SCA's training department if you want more information on Dr. Rosine's course. We have another webinar coming up next month. The topic is Carbon Neutral Fuels, the Value Proposition. And our speakers at that webinar are Dr. Christine Economides and Dr. Dimitrios Hazegnatou, both talking about carbon neutral fuels. So due to the pandemic, we've started a series of offerings of our classes in live online format. These classes are offered virtually in half days and generally offered in the morning in North America time, but they can be adjusted for different time zones if it's appropriate for your business hours. We have Larry Lake and Jerry Jensen teaching managing mature oil fields with capacitance resistance modeling. We have Dr. John Lee teaching production forecasting for low perm reservoirs. We have Amy Fox teaching reservoir scale geomechanics. And we have Leo Rothart and Garrett Knitters teaching a well stimulation workshop, practice and applied. So look to SCA for all of your needs with regards to training, consulting, projects and studies, and direct hire services. And so I'm going to give the presentation rights back to Dr. Rosine. There we go.
Thanks very
And
much, Susan.
we can see your slides.
Excellent. I'll start from the beginning. Well, thanks very much. Thanks very much for coming today. I'm John Rosine, President of Basin Dynamics, and I'd like to talk to you today about deepwater sedimentation, processes, deposits, and unknowns, as well as some of the merits and limitations of applying these types of workflows in the energy industry. Here are the objectives for today. I'd like to offer some observations and clarity on what is deepwater sedimentation and why should you care about it? What are some typical deepwater rock types, their scales and geometries? What are some typical deepwater depositional environments? Before we get into our first case study coming to us from the Taranaki Basin in New Zealand, we'll then discuss what are the fundamental building blocks of deepwater environments, including the sedimentation units themselves. Our second case study comes from the deepwater petroliferous Gulf of Mexico. Then we'll bring it all together, examine how to learn more, and then have some closing conversations. First, what is deepwater sedimentation? It's the origins of sediment and its transport and deposition in areas below wave base. This can include areas such as deep lakes. There are multiple types of sedimentation that can occur in deepwater areas, including pelagic and hemipelagic, direct suspension settling of fine-grained sediment, or due to lateral advection. You also have sediment gravity flows, flows in which gravity pulls on the solid particles, pulling them downslope. There are additional mass movements, including mass transport, slides and slumps as well. And there are also bottom currents, including contour currents. There are numerous applications for skills in deepwater sedimentation, including natural resource exploration and extraction, including oil and gas, offshore wind, CCUS, geothermal, you name it. Deepwater sedimentation can also help predict when environmental hazards might occur, such as landslides, as well as mapping the distribution of microplastics in deepwater submarine fan environments. Lastly, deepwater sedimentation is very important to basic science. And did you know that some of the channel systems on Mars resemble the sinuosity and geometries of deepwater submarine channels? Because we have limited time today, one of the areas we'll focus most on is the area of sediment gravity flows, which is a key part of the course with Subsurface Consultants and Associates this October. What are sediment gravity flows? They're driven downslope by the excess density of entrained sediment in seawater. It's gravity acting on the solid particles, pulling them downslope, making them bottom-hugging currents. Because they're so rare, destructive, and difficult to monitor, much information we get on them is from modeling them in flumes and in tanks. We can also deploy instruments in modern submarine canyons, such as Monterey Canyon, shown at the right, and we'll take those data and numerically simulate sediment gravity flows, looking at their erosion, transport, and depositional patterns. But by far some of the most important information we can get on sediment gravity flows in their deposits is through the rock record, cores, logs, thin sections, even seismic data. We can use the patterns and fabrics preserved in the rocks to recreate what are the processes of sedimentation in order to map their distribution in 3 dimensions. One of the most important questions is, how do you simultaneously and at various scales observe sediment gravity flows in their deposits to make informed business decisions about their distribution in the subsurface? Two of the most distinguished in their pursuit in understanding sediment gravity flows in their deposits are professors of geoscience, Don Lowe and Steve Graham. They've made numerous contributions not only to California geology, but also around the world. However, there are a few tricks they didn't have until late in their careers that we employ all around the world today. And one of those is the ability to use drones to map large-scale deepwater outcrops. We also employ a number of big data advances in interpreting petrography, geochemistry, and uranium-lead detrital zircon geochronology to look at source-to-sink patterns in deepwater systems. And finally, like we're doing today, we can share information very quickly via the web, such as over Zoom meetings that we've become accustomed to during the COVID pandemic. But let's talk about some of their key contributions they've made to deepwater sedimentation. And the first is the understanding of lithofacies, lithozomes, or mappable rock units. One of the first questions I'll get in my class is typically, well, what are some deepwater rock types we could expect to find in our basin of interest? And depending on grain size and type of flow, there are at least about 10 different mappable rock units you'll find in deepwater areas. And those include rock types such as matrix to class supported conglomerate, mudstone, thick to very thick bedded sandstone, all the way down to thin to very thin bedded sandstone, mudstone, and then some of these chaotic deposits such as slides, slumps, injectites, and extrudites. Now, these are third order architectural elements. So the next question I'll often get is, well, how do these scale up to higher orders of deep water architecture, and how are they subdivided into their basic building blocks? This brings to us architectural element analysis. Lithofacies are third order architectural elements. They can scale up to higher orders of genetic elements such as channels, lobes, and all the way up to submarine fan scale. And they can be subdivided into their individual beds or sedimentation units deposited by one flow, and then further subdivided into first order architectural elements, which would be something like a Bauma TB or planar laminated interval in a turbidite deposit. It's not alien to geoscientists, but one way to get more information on this question of how to map and interpret sediment gravity flow deposits is to lay a carpet of studies around the world. One, to observe the range and variability in deep water rock fabrics, and two, to get to collaborate with as many different scientists and industry centers. Here's some of the major fabrics you'll find in deep water environments. Those deposited through fluid turbulence or turbidites, those that feature matrix strength and transport as cohesive laminar debris flows, forming debrites. Transitional flows, which combine a mix of matrix strength and cohesion and fluid turbulence during their deposition. And then lastly, sediment gravity flows or turbidity currents that combine with other types of derivatives of processes from waves and rivers and tides, and even bottom currents, forming hybrid types of beds. And this couldn't be more important because the way grains come together and their sorting and grain size distribution determines their rock quality, their porosity and permeability. And this diagram, built on some of the great work of the late Professor Roger Slatt, shows some of those relationships for those rock types we just looked at, with the coarse grained turbidites, the classic turbidites, and the reworked turbidites showing very high rock quality of their initial estimates. And then some of the transitional flow deposits, debris flow deposits, and then the ultra low density turbidity current deposits showing relatively low rock quality, so likely won't behave as high quality reservoirs. And the third reason we want to lay this carpet of studies is to be able to map deep water depositional environments and build models in the subsurface. And wherever you go around the world, whether it's a passive or active margin along a compressional, extensional, or transform type regime, you're likely to get at least three major types of basin margins or continental margins. And the first is graded or in-grade continental margins. Typically, these are thermally mature, they're concave up, they can feature very long and extensive submarine fan environments that are quite mud-rich. You can also have above grade or step margins, typical of passive margins undergoing large-scale faulting due to delta collapse. Here is where you have both low gradient and high gradient intervals which can act to trap sediment on the slope and it will never reach the basin floor. And lastly, on the far right are above grade ponded or perched types continental slopes, which is very similar to our central Gulf of Mexico slope, in which flows enter mini basins and deposit sediment there, and it never reaches the deep water basin floor. What you'll notice in these different types of models is that there are about 5 main types of deep water and depositional environments. And we'll get to a 6th by the end of this talk. But as you can see, most of deep water is actually quite boring. A lot of it's overbank. But there are very interesting areas such as canyons, channels, lobes, and levees, which we'll discuss next. Canyons are the potentate feature in a submarine fan depositional system. They often fully confined flows, being at least a mile or two in depth, and upwards of 10 to 20, if not 30 miles in width. And there are at least 3 major types based on global studies around the world. Single thread canyon systems established at major river mouths, such as the Congo Canyon shown here, which that canyon head actually incisors the Congo River Delta. Second, tributary fed branching canyons with fault controlled organization. This example comes to us from Monterey Canyon, offshore California. And last, large-scale canyons constrained by mobile substrate due to mud or salt diapurism. And this example is from the Mississippi Canyon. Canyons can be filled with a number of different types of deep water sedimentary rock types, and even shallow marine. This example on the far right is from the Monticello Dam section of the Venado sandstone, showing a vast distribution of conglomerate, different types of sandstone, and mudstone intervals. And did you know this is one of the type sections for exon sequence stratigraphy along active margins? Channels are the downslope equivalent of canyon systems. They too can provide confinement for flows or be capacitors of sediment on Earth. They can be braided, sinuous, meandering, take a number of different shapes. They can confine sediment gravity flows due to incisional and erosional processes, typically along the slope. And then they can also confine sediment gravity flows due to growth of the levee crest above the channel thalweg, a common modeling parameter. By far and away, most energy companies have a lot more information on deepwater submarine channel complexes than most, because these form classic targets when they're in trapping configuration. They too can be filled with non-reservoir rocks like mudstone, but here's some of the models from some of the super major energy companies, including Exxon, Chevron, BP, and Shell. And they come from a number of different examples, global studies of submarine canyon channel systems, as well as those that are focused more on Angola or the Indus Canyon Channel system shown in example D. Levees are positive topographic features that naturally confine channel systems, and years ago they used to be interpreted as quite simple, merely formed by the overbanking of dilute low density flows into the overbank, thus forming levees. However, now we know there's much more diverse deposits in these types of environments. These can be formed by crevasse splays and overbank splays, sediment waves, even rocks that have flowed or slumped a little bit, forming types of debrites along their margins. So they're quite a bit more diverse than originally envisaged just a few years ago. And these too can form deepwater petroleum fields such as Ram Powell in the Gulf of Mexico. Splays or lobes, these are environments or bodies of sediment deposited in areas of unconfinement originating from areas of confinement, such as a deepwater submarine channel. And there are at least 5 types, and there's a 6th that's not shown here. Those are detached splays. But frontal splays form at the downsystem terminus of the channel environment. Avulsion splays can create a whole new channel by cutting off the downsystem portion of the channel that was previously active. Crevasse splays break through the levee and deposit in the overbank and are by far larger deposits than overbank splays, which merely overtop the levee. And then underfit flows that never really reach the end of the channel environment, that don't feel the confinement provided by the container of a channel, are known as channelized splays. Last but not least, for now, is overbank environments. And this is typically where pelagic and hemipelagic sedimentation dominates, but you can have all different types of sediment waves here, even deposits of sediment gravity flows, large, small, examples of mass transport deposits as well, and shell failure that ends up down here. These are some of the sedimentary successions from different parts along a axis of a submarine fan depositional system, and can be related back to environments such as canyons, channels, and lobes and levees and environments like that. These can form seals and overburden when you think more broadly about a total petroleum systems analysis. Our first field stop for the day is at Pukiaraway Beach, which means hill plus fern root in the beautiful Maori language. It's located in the Taranaki Basin on the west coast of the North Island, where seismic scale deepwater sedimentary outcrops extend offshore, where they've been producing gas reservoirs for decades. One important principle that all deepwater sedimentologists understand is the importance of context. And while these beds are deposited by like sedimentary processes, low density dilute turbidity currents forming a variety of traction structures in their sandy divisions, followed by muddy divisions at their top, largely interpreted as Bauma T, B through E sedimentation units. They're in different depositional environments, and they're separated by over 4 kilometers of rock. The rock at the left is from the northernmost, lowermost part of the formation, and the rock pictured at the right and interpreted at the far right is from a different depositional environment in the upper part of the formation in the southern part of the beach, known as an area known as Waikaramarama. Let's start with the big picture, going to the lowermost part of the formation at White Cliffs. These are images assembled from a flyover, creating a photo panel. And when we tend to give these images to geoscientists on our field trips here annually, we want to get really busy interpreting them, but there are a few things you can do to change them to make them more easily interpretable. And those of you that work with seismic data quite a bit will understand this. We can essentially boost the gain, removing some of the heterogeneity provided by the clouds and the differences in rock color. We start to see a richness in the data, different colors of rock, maybe due to water saturation, because these are quite porous rocks, and maybe due to lithology. There's one more thing we can do, and we take this for granted when interpreting seismic data, but we can vertically exaggerate these images too and interpret them much like seismic data. I'd like to point out one thing. In the middle part of the image, there's a thick interval of sandstone in the southern or far right part of the beach. It's about 30 to 40 meters in thickness. And as you trace that to the north, it thins, tapers, onlaps, and terminates against an underlying mudstone. This is an example of what a deepwater stratigraphic trap analog looks like. And while we take them for granted because they may seem obvious in seismic data, they're quite subtle in outcrop, but they can be used to better understand your petroleum fields. In the end, the white cliffs are interpreted as splay deposits. There are no large incisions that could be interpreted as canyon or channel type deposits, and they're arranged in upward fining cycles of broadly sandstone, muddy sandstone, and mudstone, at least 5 or 6 of those cycles. In the southern part of the beach, in the uppermost part of the formation at Waikaramarama, this is what channel margin deposits look like. And there's one other key principle, or one other key data set that deepwater sedimentologists need to make an accurate interpretation, and that's high-resolution sedimentary logs, one of the skill sets we emphasize in the course. And you notice here in these sedimentary logs, they have a rich abundance of climbing ripple cross-lamination, which has been shown around the world to accumulate in some of these channel margin type environments, such as Magnolia Field here in New Zealand, as well as in parts of the Tankwa Karoo, another very famous deepwater outcrop analog. There's one more attribute of high-resolution sedimentary logs, and that is you can take their first-order architectural elements, such as a planar laminated division, which has a non-negotiable thickness, and accumulate those thicknesses over a gross stratigraphic interval, and then plot those based on their subdivision on ternary diagrams. And what will happen is they'll start to break out their depositional environment. We dubbed this turbidite ratios. It's based on some of the earlier work from Walker in 1968, but we put to rest this idea that you couldn't use semi-quantitative stratigraphy to start to break out depositional environment in deepwater submarine fan systems that would yield more information for your stock tank initial or original oil in place equations, such as bulk rock volume and net to gross and some other parameters. Deepwater sedimentation also offers skill sets in petrography, geochemistry, and uranium-lead detrital Zircon geochronology to allow a more accurate interpretation of source-to-sink routing systems and provenance, which has implications for reservoir quality. We took data from that same formation, the Mount Messenger Formation, a very famous deepwater outcrop analog that many of you might have used already in your careers, cut thin sections, point counted the quartz, feldspar, and lithic grains, and then plotted them on a Ghazi-Dickinson point count diagram. Remember Steve Graham from an earlier image? This originated in his research group under the expert tutelage of Bill Dickinson at Stanford in the 1970s. It's still very useful today, and many of you probably use this method. This showed our data closely plotted with earlier interpretations of the Mount Messenger data, but it appears there was a mix of some of the potential basement terrains that could have sourced the sediment into the Mount Messenger system during this time in the late Miocene. So we need to move on to other skills, such as geochemistry, using major, trace, and rare earth element geochemistry to solve this puzzle. We use thorium over scandium and silicon over aluminum ratios to look at, is it a mafic undifferentiated rock, or is it more differentiated upper continental crust and enriched in silica? This too plotted in between some of the major basement terrains that form the continent of Zealandia, which is about the same size as India too. It's the 7th continent in the geological world. So this too appeared to be like a mix. Let's go to B in the southeast part of the slide deck. These are the rare earth element data. Rare earth elements are very powerful indicators of sedimentary provenance, the most far field effects. They tend to represent the muds and the silts that can travel a long distance. They can also be used in geochemical forensics studies, for example. They're very good tracers of provenance. And these two show a nice europium anomaly, but appear to show a mix between potentially andesitic sediment and upper continental crust sediment. So it appears there may be a mix, and there were active submarine andesitic volcanoes in the Taranaki Basin at this time, so we might expect that. However, the first aha moment is when you start combining or intersecting with igneous petrologists and other different study areas. So we took a cue from them and looked at some major trace and rare earth element ratios, cerium over vanadium, lanthanum over yttrium, and this revealed that the data closely plotted with the Torres composite terrain, which interestingly was one of the most uplifted terrains at this time, thus capable of eroding and transporting sediment into the Mount Messenger Depot Center during the late Miocene. There's one more skill set we need to discuss, and that's uranium-led detrital zircon geochronology. We sampled the base, the middle, and the top of the formation to try to establish what the drainage patterns could look like in New Zealand at this time. There are three things I'd like you to get from this plot. First, these samples are indistinguishable based on the Kolmogorov-Smirnov test at 95% confidence, basically meaning they're from the same parent population, or that null hypothesis can't be excluded. Second, the youngest grain is in the oldest part of the formation, which is a subtle unroofing signal. And lastly, there's a nice 105, 110 million year old peak that we believe is derived from a northern part of the South Island granitoid body, thus supporting south to north transport and not so much east to west. Further, the paleocurrents in the formation also support south to north transport. And then there have also been major canyon channel systems mapped that are aligned south to north for this same time period. So it appears that different studies are lining up together to show some of these source to sink routing patterns for New Zealand during this time. For those of you interested in provenance source to sink studies and their implications on reservoir quality of deepwater sandstones, I'd recommend everyone check out AAPG Bulletin. They've been collecting a number of different studies in this area because they realize how important it is. It's very in vogue, and it's a very useful tool for understanding deepwater petroleum reservoirs at this time. Because we discussed in length at source to sink and provenance, I want to offer a summary diagram. And this pulls together some of the more recent research in this area of expertise. This diagram shows three different provenances: volcanic, granite, and schist rock types that undergo transport through different types of terrestrial depositional systems, such as fluvial systems, aeolian systems, alluvial fan systems. They have different coastal and paralican depositional environments, such as deltas, different types of estuaries and embayments, and then alluvial fan deltas that then transmit sediment to get into deep water over different widths of continental shelf. And they all have different sizes of submarine fans. And this is the main point I'd like to make. Earlier studies coming from numerous organizations have shown that the drainage system length, so the fluvial drainage system, is about twice the length of the overall submarine fan system. And I think as more data continue to pour into this area of science today, we'll have less uncertainty on some of these scaling relationships. Now I'd like to talk about some deepwater sedimentation units deposited by one flow, one turbidity current, one sediment gravity flow. And these are some of the classic models that can be used to understand the basic building blocks of any deepwater depositional system. Many of you have probably heard of the Bauma sequence, subdivided into 5 intervals, TA through TE, representing suspension, traction, and then again suspension sedimentation, and represented in this core at the right that's oil saturated and traction structured, likely a Bauma TB through TE, missing the Bauma TA. The type section for these deposits is in a place known as Pericava or Luceron in an area of southeast France or practically in Italy. Lovely views of the Mediterranean from these hilltops. And this is up D21 road near the Col de Tourigny, which is also interestingly one of the beyond category climbs in the Tour de France. And the riders went past this in the second stage of the tour in 2020. And I'm sure many of the riders, Pogačar and Roglic and the other tour leaders and Julian Alaphilippe, were looking at these rocks saying, wow, look at those coarse grain bases, finer grain tops, and even evidence of flow vacillating, going in between the Bauma TB and TC interval multiple times in some of these bed tops, which is a very interesting point, which we'll get to next. Now, if you take a closer look at many of the sedimentation units, the stacking patterns, and the overall stratigraphy for the type section for deepwater sedimentation and the Bauma sequence, not many of them look exactly like the model proposed by Bauma. However, some of these do have thicker than usual mudstone caps for relatively thin sandstone intervals. And then they also do show different directions preserved in the paleocurrents and the ripple cross laminate intervals. So these flows were circling, reflecting, deflecting on some of the confining slopes in this Pericava outlier, which isn't too uncommon in our deepwater Gulf of Mexico halokinetic mini basins, where you have that same swirling and reflection and deflection effects. While many of you have heard of the Bauma sequence, fewer of you have probably heard of the brilliant model by Don Lowe, the Lowe sequence, subdivided into R and S intervals that would naturally precede the Bauma T intervals in the alphabet. Not too complex there. And these represent traction, traction carpet, and suspension deposits. The photo at the right from Point Lobos State Reserve, very close to where Tiger Woods plays golf, shows inverse grading. One of the few times you'll see inverse grading in deep water rocks. This is a process that's formed by frictional freezing. You too can generate this process if you have a bag of cereal with different grain sizes, shake it up real vigorously. The grain sizes that are most coarse will end up at the top, and the finer grains will be sieved down to the base. So this forms at the base of these high density turbidity currents. As these coarse grains collect near the bed, they're being sheared by the overlying high density flow and continually agitated until they finally have no more space to move, thus preserving this inversely graded traction carpet. It's a wonderful bypass surface that's often not observed in core, but when you do see it, it's very valuable to the interpretation. Geologists tend to be leery of drilling these types of deposits because all sorts of nasty things can happen to them during diagenesis, such as wholesale recrystallization of the pore space due to mobile fluids. You could get calcium carbonate deposited, sparry calcite cement in some of these beds, which can reduce the reservoir quality. They tend to behave more like sieves as opposed to nice reservoirs. Also, this slide illustrates another key point on bed amalgamation. There may have been mudstone caps, Bauma TD intervals deposited at the tops of these sandy beds that then may have been ripped out or eroded by the overlying high density flow. That's like someone ripping the pages out of your book as you're trying to read the stratigraphy, which makes the science very interesting. Or these flows could have been coming into the basin with such alacrity that there was never enough quiet time or quiet water conditions that the Bauma TDE intervals could have been formed and then lithified. So there are at least two options providing a non-unique solution here. Those two are reservoirs, but these are mostly non-reservoir. These are debrites, and these behave more like Bingham plastics as opposed to Newtonian fluid flows that we saw previously. This is provided by the sticky, muddy matrix, and oftentimes you have an overabundance of mud in deepwater areas. Deepwater is a great repository for sediment on Earth, and mud is one of those types of sediment. So you can create some of these floating gravel scenes in the Pigeon Point Formation shown at the left. Also, debrites can form just by a little bit of shocking or flowage in unstable environments. And this unstable environment pictured at the right is an ancient Lake Cretaceous submarine channel levee, which is slightly unstable just because it's maybe a fraction of a degree elevated above equilibrium that would keep it happy. But this one was prone to slippage, potentially due to an earthquake or some other type of instability in deep water. We just don't know. Larger in scale, but similar in process, are mass transport deposits. Groups of mass transport deposits form mass transport complexes. Oftentimes these have sequence stratigraphic significance, forming in the falling stage systems tract or in the low stand systems tract, likely along Exxon or ExxonMobil's sequence boundary. These can host very large blocks the size of skyscrapers or smaller blocks like is shown at the left in the Monticello Dam section of the Venado Sandstone. Those blocks are about the size of small autos. And then at right, the aptly named El Gordo bed from the Tabernas Basin, Spain, shows pervasively overturned and dismembered turbidites that were then reset into motion, forming this mass transport deposit. But what are beds like these that show evidence of fluid turbulence and matrix strength during deposition, showing some very sandy fabrics that could be high quality conventional reservoirs, and then some of these muddy fabrics that appear to have some of these contorted and twisted fabrics that look like debrites. Was Don wrong? Did Don miss something? Absolutely not. He knew that there must be beds in between deposited and controlled by matrix strength and fluid turbulence, and he called those slurry flow deposits, working them in one basin in the UK North Sea, and basically came to understand their global range and variability just from those examples. You'll have to read the paper for more information on those different types of sedimentation units described. This is one model shown here. But there are other scientists such as Peter Houghton working in County Clare in Western Ireland, one of my favorite places to go, where he saw similar fabrics of debrites and relatively clean sandstone, and they tended to form a repeating pattern. And so he dubbed those linked debrites. Then later recognized there was more sophisticated architecture to these deep water deposits, these beds, and coined the term hybrid event bed, or HEB. Here's some of the type sections for those types of hybrid event bed deposits, showing well-developed H1 and H3 divisions on the Loophead Peninsula near the lighthouse. And then as you cross the Shan Estuary, going to the south, here are well-developed other parts of that hybrid event bed as proposed by Peter Houghton. And Houghton also proposed that these form during the nascent stages of submarine fan deposition, potentially when they're being transported sandy sediment over underlying mudstones, such as the Clare Shale here, or over steepened margins, which have a lot of mud in the substrate that can be entrained and then change the flow rheology to create more of these transitional flow types of deposits. However, some scientists were working in the Deepwater Gulf of Mexico at that time, specifically the Deepwater Paleogene Wilcox trend, and found these types of deposits that weren't very similar in the channels, in the levees, in the lobe environments, even in the distal lobe fringes, and wondered, what are these deposits? Are these real? Are these artifacts? What are these? Which was a very good thing for this scientific investigation because it was something new that could be characterized and cataloged. Basically, every super major had about the same information at this time, but it was a group out of Chevron that used the term argillaceous sandstone bed, and that term stuck with these deposits that sort of have this foamy top of muddy sandstone in which the Bauma sequence is not well developed. It basically goes from Bauma TA, low S3, into these argillaceous sandstone intervals and then mudstone. And what it effectively does is it lops off a significant amount of the net in net to gross, thus lowering initial oil in place equations. Here are the porosity and permeability values for those types of deposits. They range from about 15 to 25% in porosity, but can span multiple orders of magnitude in permeability for the same bed. So here were some of those different types of facies, showing the structureless sandstone, the argillaceous sandstone, both with roughly the same porosity, 18 to 19%, but some have double-digit permeability and others single-digit, very low permeability. And so it really, you need to be careful where you sample some of these deposits because they may be radically different. But it wasn't just a story of transitional flow behavior in creating these argillaceous sandstone beds. It was also a reflection of changing provenance and source to sink routing patterns in North America at this time. So we're starting to pull a lot of things together by this portion of the talk. This shows the lower reservoir and the upper reservoir, and while there was no major change around the Paleocene Eocene thermal maximum in the silt grains, there was a large percentage decrease in the sand grains from going from quartz at 48% down to 31%. And this was taken up by a number of different types of ductile grains that could squish into the pore space, thus reducing the overall reservoir quality. These were example plutonic rock fragments, other different types of rock fragments, sedimentary, metamorphic, volcanic, that did not behave as rigidly as quartz during compaction and diagenesis. And to summarize that theme, in the southeast portion of this diagram, it shows intergranular volume and effective depth. And while the lower Wilcox lobes, or the lower reservoirs, should have had higher, they did have higher reservoir quality because they had so much rigid quartz grains in them, but should have suffered more compaction because they're lower in the Earth's crust. The upper Wilcox lobe was the one that had the more challenging reservoir quality, as you can see here. With the increasing compaction, it lowered the intergranular volume, and that's not only due to the transitional flow type behavior, but also due to the grain mineralogy. And so it posed essentially a double whammy against this type of reservoir. This couldn't be more important for those working the basin and the region that's attracting more capital anywhere in the world right now, in the Permian Basin region. This shows some of those deposits. The Joe Mill Sand from the Midland Basin, the Wolfcamp C Formation, the Bell Canyon Formation, showing a rich abundance of some of these transitional flow types Now let's go to California, those working out of Bakersfield in Kern County. The Stevens Sandstone, a classic deep water braided channel complex, which has very high net to gross in areas. But as you can see, it also has a rich amount of some of these transitional flow deposits, which if they don't form barriers, they can even just form baffles in this reservoir, challenging reservoir connectivity. As we travel the world, I think we'll see more of the range and variability in these types of transitional flow deposits. This example comes to us from offshore Qingdao in China. And these are lacustrine deepwater hybrid event beds that don't closely follow the models proposed by Houghton, Lowe, and Guy, or the group out of Chevron. So there's something different. So I think as we travel more and see the range and variability in these rock types, we'll be better equipped to anticipate where they form, how they form, and what kind of challenges they pose to the energy industry. All the depositional systems we've looked at so far come to us from fine to very fine-grained silt and mud-rich systems. And because we can't have trees in deep water environments, clay will form the cohesion that allows for banks to be stable along submarine channels. And so without that, what would a deep water depositional system look like if you don't have that cohesion that will provide the bank stability? Well, Leopold and Woolman were right in 1957 for terrestrial systems, but in deep water, we too can get deep water braided depositional environments in which we have lateral and vertical sand-on-sand contacts, and there's very little mud in the system to provide cohesion for channels to form. This example is from the Ventura Basin. There are also other examples from the Santa Maria and Los Angeles, as well as the North Atlantic Mid-Ocean Channel, parts of the Orinoco, and parts of the Lofoten Basin. So they are relatively rare because mud is often overabundant in deep water settings, but this is one example where sand is overpopulating the deep water system. These can be great for reservoir presence and quality. They can be prone to deformation bands or compaction bands. And then also from a total petroleum systems perspective, you're wondering where is going to be the seal. Let's re-inject the mudstone or mud into the system and even add some coarser gravels. What kind of deep water depositional system could we go to that would satisfy those grain size traits? And for that, we'll have to go to the Great Valley Group of Central and Western California and associated deep water rock intervals that have been translated northwards along the San Andreas in recent times that cluster along the coast. This is the Great Valley Group, and this shows some of our field stops when we take scientists out here to examine these deep water outcrops, and we can take them everywhere from canyon head to deep water basin plain, and that's why it's such a marvelous example. And we do have several class exercises in the upcoming class in October for subsurface consultants and associates that do come from these outcrops. And I'd like to focus on one final area of a deep water depositional system, one specific environment, and that's the canyon. This is coming from a AAPG GTW talk in 2018 that showed the differences in sedimentation patterns between upper, middle, and lower canyon to channel transition zone. We'll focus on the uppermost part of the canyon system because it's quite different from what we've seen so far in today's talk. And that comes to us from the exhumed outcrops of the Eocene Carmelo Formation at Point Lobos State Reserve. This is actually a very interesting story with these outcrops. Some British scientists studied this in the 90s and interpreted it to represent a formation that's about 125 meters in thickness and shows well-developed stratigraphic cyclicity with the coarse-grained conglomeratic deposits underlaying the sandstone deposits that are then overlain by the mudstone deposits, so well-developed upward fining intervals. And it's repeated a number of times rather elegantly in nature. A group of Americans came along later and said, well, we think the formation based on our strike and dip and subsurface cross-section interpretations is about 250 meters in thickness, twice the thickness that the earlier researchers interpreted, and then it shows no well-developed stratigraphic cyclicity. Clearly only one can be right, and so we mapped it in 2018 to find out who. So that's just a little teaser for the upcoming course. We do have an exercise or two devoted to these outcrops in the course in October, and so you'll have to come to that to find out what is the answer. But I would like to show some of the sedimentation patterns and lithofacies common in the Carmelo Formation. The conglomerate and sandstone intervals that are thick to very thick bedded individual beds lenticular, commonly truncated, eroded, and not very laterally continuous. And they do show evidence of structuring and interacting with the fully turbulent flow. The gravelly intervals are dune scale cross-stratified, even sweeping cross-stratified, and same thing with the sandstone intervals. Previously, they were interpreted as massive or structureless, but if you take a closer look, many of them, as some of the earlier researchers have shown, they are strongly structured. So likely low R1 and R2 and low S1 and S2 type subdivisions for the conglomerate and sandstone. Once we get into the medium to thin to very thin bedded sandstone and mudstone, they show different sedimentation patterns. They're partial Bauma sequences. And then I'd like to draw your attention to F, which shows what the muddiest portions of the submarine canyon fill look like. These are individual Bauma TCDE intervals, ripple cross laminated, and then having muddy tops. So what this indicates is by having a lack of hemipelagic and pelagic sedimentation anywhere in the exposed outcrops, it shows that some of these canyon systems are always on, always receiving these sediment gravity flows, and in this case, turbidity currents in their deposits. Deepwater sedimentologists have used diagrams like these for years. Now they've been updated, but they show what kind of first-order architectural elements you should find from deepwater canyon head to basin plain as you go along the axis of the depositional system, showing overall generic flow models, showing the different abundances of different first-order architectural elements, turbidity current dominated models, and then debris flow and transitional flow models. So not knowing much about the basin, this is always a good place to start to anticipate what kind of rock types and lithofacies you'll find from those different areas based on water depth in the system. But this does not take into account bottom currents or contour currents. What if you have flows that are moving across the slope in the deep water realm, transporting and moving sediment along topographic contours? Well, you can end up with classic bidirectionally graded contourite beds such as shown at left. Or if you have systems like in the Tabernas Basin in Spain, you have downslope sediment gravity flows and then also along slope flows that are reworking those same deposits. And so what's happening now is a particularly humble time for many deepwater sedimentologists is that many of our models are getting redrawn, showing the effect of contour current sedimentation and processes on some of these previously envisaged just downslope dominated submarine fan environments. And what these contour currents have the power to do, some of them can be quite robust and powerful, forming large-scale dune-scale cross-stratification. This tends to push the sediment in the direction of the contour current. However, sometimes it will lead to a relatively small and anemic levee on the flow side, and that will cause the slope channel to move in the direction of the contour current, or opposite the direction, against the direction of flow. And probably the best and most detailed and best characterization of these types of deposits around the world, because they have studies all around the world, is coming to us from the Drifters Research Group at the Royal Holloway, University of London. And that's many of the studies shown here at the right. I hope you've enjoyed today's talk about deepwater sedimentation. If you're interested in learning more, there are a number of ways to get involved. You can join our hands-on course on deepwater sedimentation this October. Feel free to schedule a consultation, go to a conference. GeoGulf is in Austin this year. Join a research group, subscribe to a journal. And then one of the best ways, I think, to learn hands-on and apply these concepts to your petroleum fields is to go on a field trip. And even during times of COVID, there are safe ways to lead field trips, and that's captured in this GSA Today cover article, Field-Based Geoscience Education. I hope everyone can have the time to read it. Well, thank you so much today. It's been great to get to talk about one of my favorite subject areas in geology, deepwater sedimentation. I hope you've learned a lot and hope to see you this October.
Thank you, John. The questions are starting to come in now. I want to remind everyone you can type your questions in the GoToWebinar question feature and you will be anonymous. Later today, you'll receive a link to a recording of today's webinar, an evaluation form, and a link to registration details for Dr. Rosine's class, Applied Deepwater Sedimentology and Stratigraphy, which is offered October 11th through 15th in Houston, Texas. So the first question is for the turbidites or debris flow outcrops, how much geologic time is encompassed per section? These appear to be very thick deposits.
That's a really good question. And it varies based on which outcrops you're talking about. It always helps to have constraint, biostratigraphic constraint, direct age dates, potentially from an ash bed to constrain sedimentation rate. Oftentimes I find that in the studies, sedimentation rate is not very well constrained, and so it can appear to be extremely high or extremely low. But one question I'll often get asked is, well, how long does it take to deposit a bioma-sequenced bed, TA through E, that's about a ½ meter in thickness? And the answer there is instantaneously for the TA or S3 interval. That's basically just suspension collapse from a fully turbulent flow. And so that's very quick, and even for geologic time. And the planar laminated and ripple cross laminated divisions can take minutes to maybe a few hours, depending on how thick that sedimentation unit is. But these are relatively quite brief moments in time in which these sedimentary layers are being deposited. I think we'll know more as more and more types of equipment are deployed in submarine canyons, the Congo Canyon, the Monterey Canyon, places offshore British Columbia, to really constrain how long these sediment gravity flows operate and how long they'll deposit sediment. I think that's one great question and a great area of future research. So expect those answers to change, I think, over the next 5 to 10 years. That's a very good question.
Thank you. So you mentioned there were 5 or 6 types of splays or lobes. How often do these splays tend to be hydrocarbon bearing?
Oh gosh, probably as much as any different type of canyon or channel or any other deep water deposit is hydrocarbon or petroleum bearing. That I would have to defer to my petroleum systems friends who model source rock charge, access, timing, maturity, because it depends more on those factors as opposed to just these how the sediment's distributed in the deep water realm.
Sure.
And what these deposits look like. So
Probably
I think
depends on reservoir quality rock.
Yeah, you could have a wide range. And then if it is poor reservoir quality, it could have trouble getting charged, especially if you have really large or sticky or big molecules versus gas.
So the next question, the model of the contourite stratigraphic section looks a lot like the models for hypersinites. Is the big difference the overall thickness?
Could be. Can you define hypersinites?
Our questioner didn't give that definition.
Yeah, I'm unfamiliar with those. So maybe if they could provide a little more information, we could
Maybe I've
provide some
misread it.
similarities and
Could be
differences.
hyperpyrite. I'm not Pycnite. She's pronouncing it wrong. He said
Hyperpick Knights.
Hyperpick Knights. Thank you.
Potentially. Okay, yeah, everyone's
Yes,
getting a new lexicon and deep water terminology nowadays.
exactly.
Good question. Hyperpick Knights, they can look like this. There aren't a lot of highly detailed models on the sedimentation in some of those. Recently, there have been some, but I think detail in those models can come a long way. They do have very similar sedimentary structures to regular turbidity current deposits, but it really depends on the nature of the type of hyperpycnal flow and what kind of sediments bringing with it, and they can be quite diverse. It's an area that hasn't received a lot of attention from a lot of researchers around the world, but I think that's an area of research that we could go more into.
So next question, how can you effectively model frontier offshore areas with only limited seismic data sets?
Boy, that's a really good question. That usually takes whole teams of engineers, geophysicists, geologists, a few months to a few years to make good business decisions. Some of the skill sets we discuss in deepwater sedimentation can be applied directly to new ventures and exploration workflows. Yeah, they'll have to be a little bit more specific on the question on that one, because that's going to involve a whole team. So, but in these classes, you'll learn the skill sets from specialists and deepwater sedimentary specialists, but then you need to involve a whole team, your petroleum systems team, your geophysicists, your geologists, your biostratigraphers, definitely.
The
So
geochemists.
right, it involves a whole lot of skill sets to make those important decisions. Certainly couldn't be done by one person, but you will find skill sets in this course that will directly apply to those aspects of deepwater sedimentation, the range and variability that you will see in those environments. But yeah, if you could be more specific on the question, that would help too.
Okay. Next question. So you mentioned the use of ternary diagrams to look at turbidite ratios. Could you talk more about that?
Oh, that's great. Yeah, it's a question I often get asked. So in generating those, I find that in some basins, there will be very coarsely measured stratigraphic sections, and some teams can go through and measure a whole lot of stratigraphy, kilometers and kilometers, and get the basic picture right. I find very interesting results come from some of the details. And so most of my measured sections go down to centimeter or sub-centimeter scale, where you can capture the true range and variability in the sedimentary structures. And from that, you can generate a very high quality semi-quantitative data set on the thicknesses of those different sedimentary structures. And turbidite ratios takes basically all those thicknesses, plots them in Excel workbooks and on ternary diagrams, and finds out that, well, each one of those points is roughly 10 to 20 to 50 beds, and those will reveal different types of depositional environments in deep water. And so it's really only available if you have high resolution measured sections, but it can be very telling when you're wondering how to use core data to figure out what are the depositional environments, what are the bed lengths, what could the bulk rock volume be, and how can we accurately model net to gross. Just like with any data set, there's uncertainty, but I think more of these different methods you can apply to one field or one business opportunity, the lower uncertainty you'll have overall. But yeah, turbidite ratio is very exciting. I think it's expanding more to different types of depositional systems, fluvial, shallow marine, lacustrine, to see what they can find in their types of depositional environments. But for this class, we'll mostly be using that technique to look at deep water rocks.
So you mentioned you would be talking about 5 types of environments plus one more. So what were the 5 types, just in summary?
Great point. So there's a lot of confusing terminology out there. But if you go anywhere around the world, there are typically 5 main types of deep water sedimentary environments that companies would use on GDE or EOD maps in exploration workflows. So gross depositional environment maps or environment of depositional maps, depending on which company you're at. And those will often be grouped into canyon environments, channel environments, levees, lobes or splays, and then overbank. Those are the big 5. But what's recently come into play is a recognition of drift and mound type environments. And one of the great papers on that is by a scientist named Amanda Thron out of University of Sydney, who cataloged over 267, I believe, contourite drift or mound deposits around the world, because more and more companies are going to these areas, offshore Canada, the Atlantic margins, offshore Eastern Africa, offshore Mozambique, ENI's big discovery, Coral and Mamba. Some of these are these hybrid sediment gravity flow and contour current mixed depositional systems. And I think there's a few conferences coming up on it. Once we can have conferences again, one's coming up in Lisbon in May, discusses these topics more in detail.
Excellent. Thanks for that summary. So thanks to everyone for attending today's webinar. Later today, you'll receive a link to the recording of the webinar and registration details for Dr. Rosine's class with SCA offered in October in Houston. Thanks for joining us today. Goodbye.